In this lecture, we will cover the common Opamp topologies. Using these topologies, we can create a diverse range of circuits for different applications easily. Alright, let us start with the analysis of this inverting amplifier topology. Here, I will have 0 volts due to the ground, and that will be reflected to this inverting input as well. And if I were to write the KCL for this node, I end up with 0 minus V in divided by R1. That's the current flowing this way. I know 0 current is flowing this way. And plus the current flowing this way. 0 minus V out divided by RF is equal to 0. From here, I calculate V out as RF over R1 with a minus sign times V input. So in other words, the output is a gain RF over R1 times V input, and we are also changing the sign of the input. So whatever is plus will become minus, and whatever is minus will become plus. Now I have the non-inverting amplifier. Here I have V input. Therefore here I will have V input as well. And since there is no element in between, at this point I will have V input as well. And what I see is here the current flowing this way will be equal to 0. So therefore this part is a simple voltage divider consisting of RF and Rin. Therefore I can simply write Rout as RF plus R1 divided by R1 times V input. I can also write this as 1 plus RF divided by R1 times V input. So here the difference from the inverting amplifier is we don't have a negative sign. So the sign of the input is the same of the sign of the output. However, here we observe that the gain will be always greater than or equal to 1 because the resistor values RF and R1 will be positive, and we have 1 plus this positive value. Alright, let's have a look at this circuit. Here I have V in, and therefore here I will have V in as well. And since this is directly connected to the output will be equal to V in. So at first look, this circuit looks useless. It takes an input and it makes it an output. So why do we use these circuits? Imagine I have here two circuits. Circuit 1 and here circuit 2. And these are connected. Indeed, let's assume that here at the bottom they are connected through the ground. Now, the circuit on the left might be a sensor, and circuit on the right might be a measurement circuit. Obviously, I don't want my sensor to be affected by the circuit 2. So I want it to be isolated. I want circuit 1 to affect circuit 2, but I don't want circuit 2 to affect circuit 1. But obviously, the changes of voltages and currents in circuit 2, if these circuits are connected to each other using simple wires, will affect the circuit 1 as well. In order to avoid this, I do this. I have here circuit 1, I have here circuit 2. They are connected to each other, and in between I will be putting my buffer circuit. As soon as I put this buffer circuit, the circuit 1 is now isolated from the circuit 2. Circuit 1 will affect circuit 2, but circuit 2 will no longer affect circuit 1. So this is very useful in very many different applications. Okay, this is the summing amplifier topology. Indeed, this is the inverting summing amplifier topology. Let us try to solve this question using the superposition principle. Let's assume that I have only V1 and I want to figure out V output 1. Then this is the inverting amplifier topology, and V out 1 will be equal to minus RF over R1 times V1. Similarly, for V out 2, I will have minus RF divided by R2 times V2. And we can do this for all the inputs until V out n, the last one, is equal to minus RF divided by Rn times Vn. And if I add all of these, I end up with V out is equal to, with a minus sign in parentheses, Rf over R1 times V1 plus Rf over R2 times V2 plus plus Rf over Rn times Vn. In other words, this topology multiplies each of the input voltages with a different gain if we have different resistor values, adds them, but at the end multiplies the sum with a negative sign, and therefore it is an inverting summing amplifier. Now we have a non-inverting summing amplifier. So as the name implies, I expect it to sum the inputs and put them to the output, but without changing the sign. So let us try to analyze the circuit. I will start with defining here a node VA with respect to the reference here. And I will write the KCL for that. I know that no current is going this way. So VA minus V1 divided by RA divided by K1. I will put the K1 to this side, to the upper part. And I will continue K2 times VA minus V2 divided by RA plus K3 times VA minus V3 divided by RA. So far I found the current this way, and this way. Now I have the current going this way. Plus, now again this multiplication with this term, 1 minus K1 plus K2 plus K3 times VA divided by RA is equal to 0. Can I simplify this expression? Yes, I can, because here I see K1, K2, and K3 times VA, and here I have the same terms, but these are with negative signs, and those are with positive signs. By the way, I forgot the parentheses here and here. Now, if I simplify this expression, I end up with K1 times V1 with a minus sign minus K2 times V2 minus K3 times V3 plus simply VA. From here I find VA is equal to K1 times V1 plus K2 times V2 plus K3 times V3. Okay, this is one of the important expressions I needed to solve this question, because I know now VA. And here we will have VA as well. And since there is no elements in between, here I have VA as well. And now I can calculate V out as simply using the voltage divider rule. RB plus RB times K4 minus 1 divided by RB times VA will be equal to V out. So I can get rid of the RB terms, and here I have RB subtracted by another RB due to this minus 1. So this whole expression will be actually something very simple. It will be K4 times VA. And if I use VA in equation 1, in this equation I end up with V out is equal to K4 times, in parentheses, K1 times V1 plus K2 times V2 plus K3 times V3. So I have right now the output equation for the non-inverting summing amplifier. However, we need to be careful. So let's have a look at this term. This term is a resistance value, RA divided by this constant term. And if K1 plus K2 plus K3 is greater than or equal to 1, then this expression will be negative. Therefore, since we cannot have a negative resistance, K1 plus K2 plus K3 should be less than 1. Okay, and since I have here RA over K1, so K1 should be greater than 0, K2 should be greater than 0, and K3 should be greater than 0 as well. It's another condition. And the third condition is related to this part here, such that I don't have a negative resistance. K4 should be greater than 1. Now we are seeing that we have the output, but this output should satisfy these condition 1, condition 2, and condition 3. Here is the difference amplifier. Let's see how it works. Again, I have no current flowing in this way and no current flowing this way. Let me try to figure out the VA. If I have here VA, I will have here VA as well. I will find simply VA by analyzing this part of the circuit. VA will be equal to R2 times R2 plus R1 times V2, voltage divider rule. And now let me try to calculate V out as a function of VA and V1. So what will that be? Let's write the Kirchhoff's current law. Current is going out this way and current is going out this way. VA minus V1 divided by R1 plus VA minus V out divided by R2 is equal to 0. Let's simplify further. R2 times VA minus R2 times V1 plus R1 times VA minus R1 times V out is equal to 0, but we can simplify this further. V out is equal to R2 times R2 plus R1 times VA minus R2 times V1 divided by R1. Now let's take this expression for VA and put it into this equation. V out is equal to R2 times V2. The R2 plus R1 cancelled itself with the denominator of this equation, and minus R2 times V1 divided by R1. So V out accordingly is R2 divided by R1, which is a gain, times V2 minus V1. Basically, this circuit takes the difference of the V2 and V1 and multiplies it with a positive gain and outputs that. Now here we have a voltage controlled current source. In other words, we have a voltage input here and we have the current output defined over this load resistor, and the output current does not depend on the value of RL, but it depends on the input voltage Vin and this resistor value. So let's see how this circuit works. To say the truth, I don't know, so I will start with defining some nodes. I will call this V out, and I will call this as VA. And I can write the KCL for VA. VA minus V input divided by R1 plus VA divided by RL plus VA minus V out divided by R2 should be equal to 0. Of course, I assume that no current is flowing through the input terminals of the operational amplifier. Now, what other equation can I write? Here I have V out, here I have ground, and no current can flow through here. So in other words, I have a perfect voltage divider, plus if I have here VA, I will have here VA as well. So then I can relate VA and V out. VA is equal to R1 divided by R1 plus R2 times V out. So this might be quite useful. I can also write V out is equal to 1 plus R2 over R1 times VA. So let's see what we can do with these equations. One of the things which I can do is that I can take this expression and I can write everything in terms of VA in this first equation. Okay, let us try to write wherever I see V out this expression here. So VA divided by R1 minus Vin divided by R1 plus VA divided by RL plus VA divided by R2 minus 1 plus R2 divided by R1 times VA divided by R2 is equal to 0. Alright, so what can I do here further? So let's expand this term and rewrite this. VA divided by R1 minus Vin divided by R1 plus VA divided by RL plus VA divided by R2 minus VA, this is good because I will subtract it from that other term, plus, minus VA divided by R1 is equal to 0. Let's do some careful accounting. This term cancels it with this term. This term cancels itself with this term. And I end up with VA over RL is equal to Vin divided by R1. From here I find VA is equal to V input times RL divided by R1. This is good because I know from here I out is equal to V input VA over RL. So I will write I out is equal to VA over RL, and accordingly this will be equal to Vin over R1. Indeed, the output current is equal to Vin over R1 for this circuit. So we have derived the constituent relations for the voltage controlled current source operational amplifier circuit. So in engineering systems, we represent the behavior of systems using block diagrams. Block diagrams describe the mathematical relations between the input and output, and they are very convenient because then instead of looking to lots of equations, you can look at a number of blocks, visualize them easily, and that way understand them in a short time. There are lots of software packages which are tailored for visual programming using block diagrams, such as MATLAB Simulink or LabVIEW. But now we will cover block diagrams from a theoretical point of view. So what do we have here? Here we have a input signal x, which is multiplied by the constant 4, and the output becomes 4 times x. On the right side, we have a summation operator with the summation block, which adds all the signals entering to this block. 4x minus 5 plus 2. Accordingly, z will be equal to 4x minus 5y plus 2. And we only don't have to have these simple summation or multiplication blocks. We can have any type of blocks, such as a derivative, integral, and so on and so forth. So it is also possible to connect the block diagrams. Here I have a block which takes the input x and outputs 4x. Another block which takes the input y and output minus 5y. And here I have a constant directly entering to this summation block. And the output z will be again 4x minus 5y plus 2. Now, once we have the block diagram representation, then we need to use some of the hardware or software tools we have in order to implement these block diagrams. And one way to implement these block diagrams is to use our electronic signal processing tools, which are the operational amplifiers. We will use operational amplifiers to implement these block diagrams. For instance, here we have a gain of 4. It takes an input and multiplies it with 4. And we can use for this the non-inverting topology and have some type of resistor value here. Usually we use 10K or 20K. And then we will need to calculate the gain for 20K. So if we want to have a gain of 4, our F should be equal to 60K. And accordingly, we end up with our 4 times Bx implementing operational amplifier circuit as shown here. The second operation is multiplication with minus 5. For this, we will use the inverting topology, where the output is equal to minus Rf over Ri times V input. So I will again take the 20K resistor value here, and for a gain of 5, I will need to have here 100 kilo ohms. So in general, when I do circuit design, I try to use the common resistor values like 10K, 100K, and I try to have one of the values as the most frequent value used in that circuit, such that when I implement it on a breadboard, it is easier. And accordingly, here I have my operational amplifier circuit, which takes the input Vy and output minus 5Vy. However, we need to be careful here. We cannot input 500 volts and get minus 2500 volts out. The operational amplifiers have the saturation voltage. For instance, for plus minus 15 volt supply, that is plus minus 13.6 volts. And we need to be very careful that every operational amplifier in the circuit works within this range. If they are saturated, the output operations will be not correct. Now, in order to implement the summation operation, I will be using the non-inverting summing amplifier topology. And let us remember under which conditions we can make this circuit work. K1 plus K2 plus K3 should be less than 1. K1, K2, and K3 should be greater than 0. And K4 should be greater than 1 as well. Okay, K values are positive. K1 plus K2 plus K3 should be less than 1. So let's have the gain of 1 over 4 for K1, K2, and K3. Then the summation of them will be 3/4, and it will be less than 1. However, now I have multiplied the V1, V and V2 with 1 over 4. I can make the general gain is equal to 1 by making K4 is equal to 4. So in other words, V out will be equal to 4 times 1 over 4 V1 plus 1 over 4 V2 plus 1 over 4 V3, and this way the output will be the summation of V1, V2 and V3. Now what should be those values? Let me start with my most frequent value again. Here I have 20k. In order to have k is equal to 4, here I will have 60k. Now let's look to the other side of the circuit. Let's assume I am also using 20k for the R. I have the K1 value of 1 over 4. So let's assume that here I have 20k. All of them will be equal to each other because they are being multiplied by the same 1 over 4. And if my k is equal to 1 over 4, I have here 1 minus 3 over 4, which is 1 over 4 as well. And since I chose originally the RA value of 80 kilo ohms, this expression will be equal to 20k as well. At the end, I have a circuit which has bunch of 20k resistors and one 60k resistor, and the gain from the input to the output is 1, and I just sum all of the inputs. Now that I have designed all the individual components, in order to realize my algebraic operation circuit, I need to combine the individual parts. One of those parts is here. This is taking Vx as input and outputting 4Vx in a non-inverting amplifier topology. The second part is here. We are taking the input of Vy and outputting minus 5Vi with the inverting network topology. Then we have the DC voltage 2 here, and all of this is connected to the non-inverting summing amplifier, and at the end I have 4Vx minus 5Vy plus 2. So this realizes my circuit. So in the future, once we have energy storing elements such as capacitors and inductors, we will have much richer behavior, and we can even design controllers, PID controllers for robots using these circuits. Now let us look at one more little point. Why does this work? This works because the output of an operational amplifier here is not affected by the input voltage of another stage. So in other words, the operational amplifiers are isolating each other from the operations they do. Only the output of one operational amplifier affects the input of the other one, but not vice versa. So this concludes this lecture then.